Thank you, Bill. It's, of course, a pleasure to be here again. I was here just a few years ago, actually. Was anyone here then? No?
We changed the whole department.
The whole department. Well, yeah, Carl Tarikian invited me, who, alas, is not here anymore. So, anyway, it's good to come back. I'm looking forward to spending an interesting remainder of the day, and tomorrow morning I'm here as well. So when I decided, Bill invited me, I gave him a few topics that I could talk about, and he chose this one, which is one that I actually haven't really given a talk about yet before, because usually when I get invited places, they want to hear something that's specifically about North America. But we do a lot of work on other parts of the world as well, so I'm going to be covering quite a bit of the world today. And but because this is the first time I've given this, I'm going to be as surprised as you when I see what's on the next slide, because I put this together in rather a hurry because of all sorts of other things going on. But it's a pretty large group of people we have at Lamont who have been working on aspects of decadal variability for several years now, and there's some they're all listed there. Colin, Wen, Chang, and Sloan are three PhD students whose thesis touch on various aspects of this. Colin has already graduated. Wen, Chang, and Sloan are still there. And also a load of people at the International Research Institute for Climate and Society, which is on the Lamont campus as well. Okay, and mostly it's funded by NOAA, NSF, and Department of Energy. The NOAA award is unfortunately terminating. Despite the success of 3 years of research and 50 papers, they terminated the program. And please do not ask me of my opinions about NOAA. So, on we go. So before I get on to the topic of decadal variability, I don't want to be accused of only talking about thinking variability matters and climate change does not matter. So let's get that out of the way right now. Hydroclimate around the world is going to change as a result of rising greenhouse gases, and this has been known for several years now. But it was the most recent IPCC, the IPCC Assessment Report 4, based on CMIP3, that this really started coming out and getting a lot of attention on top of all the attention that was being paid to temperature changes. And the new one that is coming out soon, AR5, based on CMIP5, the results are essentially very, very much the same as what you get from CMIP3. And the global patterns are shown here in terms of precipitation minus evaporation. So that's the net flux of water at the surface of the Earth. And the map on the left is, I believe these are CMIP 5 results. The map on the left shows what P minus E is now, together with lower tropospheric flow fields, the wet ITCZ and monsoonal regions, the very dry subtropics, and wetter regions in the high latitudes. And you can see the flow converging from the trade winds into the wet tropical regions, and you can see the flow diverging away from the dry subtropics and converging again into the higher latitudes. That transport of water vapor explains why we have this banded structure of P minus E around the world. And then the one on the right is the change averaged across a whole load of these models for the next 2-decade period relative to the second half of the 20th century. And you can see that to first order, you will get areas that are already dry become drier, areas that are already wet become wetter. So the subtropics dry and the deep tropics and higher latitudes get wetter. Less obvious there, but is that there's a poleward expansion of the subtropical dry zones as the storm tracks retreat poleward, the Hadley cell expands, and so on. That's what models project that will happen. That's a multi-model mean, so you don't see any real component of natural variability there. That's just the radiatively forced component. So there's a couple of questions that immediately come to mind from that. Is this happening? Is this a change that is already underway? And even if it is already underway, how important are these hydroclimate changes relative to the variability that will happen on these time scales. So the decadal variability that just occurs from natural oscillations of the climate system. So that's pretty hard to tell whether it's happening now when you look at precipitation trends. I've plotted, this is all based on GPCC station data, and there are two different trends there. One at the bottom is 1979 to 2007. That's a time period that is often used post-1979 because of the 1979 is kind of the beginning of the satellite era. It is the beginning of the satellite era for precipitation, and many reanalyses begin in 1979, like the ECMWF one. So that's often used as a time. And if you look at the trends over there, you see that there's a considerable drying of Western North America, for example, that has occurred since 1979. And that was one thing that was in the article in the New York Times today. But then if you look at the longer period, 1901 to 2007, you don't see that in the Southwest. So over a very long time scale, you don't really see much evidence that Southwest North America actually is drying like the models predict it should do. But then over the shorter period, you find that you do see a drying. Well, the reason for that is that when you're looking at these long trends, it's different sampling of the decadal variability that is giving you different trend patterns depending on when you start the data. Look at the Sahel region of Africa, for example, where you've got a wetting trend since 1979, but if you look at the whole period, you've got a drying trend there. Again, that's just because of different sampling of the natural decadal variability. Okay, so what we're going to talk about now is, for the rest of the talk, is this decadal variability. And in one little bit more climate change comes in, but mostly I'm just going to talk about natural decadal variability. So to my mind, the reasons for being concerned with decadal variability are it has to be clear to anyone who's old enough to live through it. It has to be clear in your day-to-day life that this has actually happened. And it should not require any fancy statistics to see it. So if you can only see this through some fancy singular spectrum analysis, then forget about it. It's not going to matter for anything. And it should have some pretty clear consequences to the people who are actually living through it. That turns out to be true for much of the world. I remember when I arrived here in 1983, I was at GIS, and my advisors were David Rind and Jim Hansen. And one of the things that Dave Rind said to me in the first months of being there was that in New York City, where we were and where I still live, there's about, since the early 1970s, there's been about a 25% increase in precipitation relative to the earlier part of the 20th century. And I'm going to get back to that because we'll talk about that. And that actually really struck me that was the case. And I'm rather glad that eventually, some 30 years later, we actually did look at that problem. But it's something that everyone who is old enough, I moved to New York in 1983, so it was too late. But for someone like David or anyone else who is a New York City resident who's old enough knows that. It just was obvious that if you lived through it, that it suddenly got wetter in the early 1970s. And there are some other common examples as well. So, so based on this principle that if it's worth analysing and of importance, then it's got to be obvious. The analysis that will proceed will be entirely based only on maps for particular times and time series, and some model simulations and some observations, but all based on maps and time series, based on sheer simplicity. And this is the Americas part of this is going to be appearing in a book chapter that will be published later this year. So two parts of North America we'll talk about, and then northeast Brazil, the southern part of South America, the Mediterranean, and East Africa. So
along these lines of defining trends, can you define for me decadal variability? Because I've seen the term used 1,000 times, but I'm not quite sure how you define it. Does it have to have a 10-year peak?
No. All I mean, no. No, all I mean by
Interannual?
all I mean by that is some decades are distinctly different from other decades. It doesn't have to have a particular peak in the spectrum. It could come about from rectified interannual variability, but an average over one decade is going to be notably different from an average over other decades. But it's a very imprecise definition, but it doesn't have to refer to a spectral peak. So it's variability, not necessarily an oscillation. Okay, so these are all pictures of decadal variability, and we will get to them bit by bit. You can guess as to where they are right now. I think the one on the top left is pretty obvious. That's the Colorado River. There it is. And Mexico, it will be included in this discussion as well. And this is where we are as of now. This is the Drought Monitor on February 11, 2014. It comes out every Thursday, so that's last Thursday's. And as you know, California is going through one of the more severe droughts that it's had within the last century or more. But that is part of a general drought that is affecting pretty much everywhere west of the Mississippi River, in fact. And though not in California, much of the southwestern part of the United States has actually been in drought since the 97-98 El Nino. So the southwestern drought is now reaching about 14 years in length now. So that would classify as decadal variability. Okay. So one of the main tools we use for analyzing this kind of thing are these extensive series of climate model simulations that we do at Lamont. These have always historically been done with the old NCAR CCM3, which is a model of 1998 vintage, and it turns out to be particularly good in the Americas. We're now trying to decommission it and replace it with CAM 5.3, and we will see whether that performs as well at simulating America's hydroclimate variability as CCM3, because the intervening NCAR models, all the CAMs 2 and CAMs 1, 2, 3 were not as good as CCM3, which is why we stuck with CCM3. So all of these simulations begin in 1856 when sea surface temperature observations begin. We always do 16-member ensembles. They go up through the end of 2012 right now. We update them in about February, March, as soon as the Hadley Center releases December of the previous year's sea surface temperature, which we haven't done yet for last year. Different atmospheric initial conditions, so we end up with 16-member ensembles, and the basic ensemble is global sea surface temperature forcing, so the atmosphere model sees the sea surface temperature histories absolutely everywhere, and then we do other ones where we only change the sea surface temperatures in the tropical Pacific or the tropical Atlantic or all the tropics, and so on and so on and so forth. And what I'm showing here actually is a comparison between the soil moisture in the model, which is the blue curve in the top, and the shading around it is the plus minus 2 standard deviation of the ensemble spread. And then the black curve there is the soil moisture as simulated by the Vic land surface hydrology model at the University of Washington, where they took a land surface model and they forced that within observed temperature and precipitation. So they're taking the observed meteorology and computing the soil moisture from that. So that's like as good as we can get for observed soil moisture. And you can see that there's a broad sweep there in which the model is capturing these decadal variations, especially this very wet decades in the 1980s and 1990s, and then the dry period since then, the drier period in the 1950s and so on. And some of the year-to-year peaks are being captured there as well. And you can see from the picture below that much of that is actually being dictated by the tropical Pacific sea surface temperatures. So that's not the only story for the southwestern part of North America, but the tropical Pacific is by far the biggest part, giving the variability on the interannual timescales and then going out to these decade-to-decade swings as well. Previously, we've tended to show these pictures for precipitation, but this one is directly more hydrologically relevant in that it's actually for soil moisture.
Measures of correlation that are quantitative?
It should be, it's not on there. These, I can tell you, sorry, who was the question?
Me.
They're about 0.5.
0.5.
So correlation coefficient. So it's about 25% of the variance, which is pretty high for these kinds of things. There's only about one place in the world that you can actually get above that. So it means about a quarter of the variance of precipitation, if you did it for precipitation or soil moisture in that region, is ocean forced.
There's only one place in the world where you can do this game with soil moisture and get a correlation.
That has a higher correlation than Southwest North America. Southwest North America is one of the places where the hydroclimate is most closely controlled by the oceans. Mm-hmm. Southeast South America would be another one. If you do it around here, it's essentially where we are right now. In the Northeast, it's essentially zero. Okay. So it's not, internal atmospheric variability gives you the other 3/4. Okay, so then this one is shifting from the southwest to the Great Plains. Here, actually, the correlation coefficient is almost as high. You're basically getting the same story in that the globe. Most of what the global oceans are doing is actually coming from the tropical Pacific in the Great Plains too. So if you look at take these soil moisture maps, soil moisture either for the observed one, which is the Vic reconstructed one, or for the model, which is the one at the bottom, so that's the ensemble mean, and correlate them with sea surface temperatures around the world, then you can see that big tropical Pacific, El Nino-like, when it's an El Nino conditions, in the tropical Pacific Ocean, soil moisture in the southwestern United States tends to be high. And the model just makes that it's an ensemble mean, so it isolates the sea surface temperature force component, just beefs up that correlation a little bit higher. Anything going on in the Atlantic Ocean is rather not very obvious in here. There does seem to be, perhaps the Atlantic is a little bit more influential in the southern parts of the plains and northern Mexico. But for this particular region in southwest US, that's not going to be a big part of it.
Is there an advantage of using soil moisture versus rainfall?
We have it all for rainfall as well. Rainfall actually works slightly better. You can reproduce the rainfall a bit better than soil moisture, but that could be because soil moisture data is actually unavailable, so the soil moisture is actually being computed by a hydrology model forced with observed meteorology. And soil moisture is a touchy field in climate models because models have all sorts of different depths of soil moisture. So I'm putting soil moisture there because very often if you show it in precipitation, someone who works in water resources will say, oh, that's very well, you can do it with precipitation, but what about soil moisture? So I wanted to say, actually, if you do it in soil moisture, it does work. You could do it with runoff as well. But the precipitation works, you can simulate that a little bit better. Okay, so to look at some different decades, two very different decades in the American West were the 1930s and the 1990s. So the 30s were, of course, the Dust Bowl drought. And then the 1990s were about the wettest decade of the 20th century. If we look back on tree ring records going back hundreds of years, the 1980s and 1990s stand out as perhaps about the wettest decade in a millennium in Western North America. That's a bit ironic because those were also 2 decades of, those were the 2 decades of phenomenal population growth in the southwestern part of the United States as well. I mean, and that was no doubt made a lot easier by the fact that there was abundant water resources during those 2 decades. So the top maps show the sea surface temperature for those 2, and you can see that in the 1930s, The global warming signal is there. You know, you can see that in the latter decade, it's just warmer everywhere. In the earlier decade, you can see this very weak La Nina-like state that exists in the tropical Pacific Ocean at that time, and the Atlantic was a little bit warm at that time too. We now know from all this modeling that that's an ideal state to set up dry over Western North America. The drought that occurred during the Dust Bowl was that one there, which was centered around about in the central plains, going up into the northern plains. It was not down in the southwest, and then the lower left there is what the model produces for the same thing with global sea surface temperature forcing. So it's a little bit too far south of where it actually should be and going down into Mexico. We feel we know why that is there because this model does not include dust aerosols. When we redid these simulations with a model with interactive dust and allowed the dust storms to be generated, that moves the drought. It intensifies the drought, but it also moves the drought north with the movement of the dust. So in the 1930s, unique amongst North American droughts, the dust played an added feedback. So we feel some of that difference is explainable. By contrast, in the 1990s, this was a decade which was overall El Nino-like. So you have a big, fat, warm anomaly in the tropical Pacific. And this was overall wet. So you can see for the model, it kind of just reverses the pattern that it had in the 1930s. But wet across pretty much the entire North American continent, and that matches reasonably well what actually happened in the 1990s. So these decades, and just like the El Niños and La Niñas on the year-to-year basis can influence precipitation over North America, when you look at these decade-to-decade differences that have occurred over the 20th century, it's also the lower frequency part of the tropical Pacific variability that is explaining that. Okay, so move on to the next area, which is the northeast North America. And the motivation for doing this was the water supply of New York City, which we did get a small amount of money to look at drought vulnerability and climate change in the northeast. So New York City draws its water from the Catskill Mountains, which are, where's the thing on here? Ah, there they are. New York City's down here. And the Catskill Mountains are about 100 miles northwest of New York City. The first water supply came from the Croton watershed, which is in suburban parts of area north of New York here. And then in the early part of the 20th century, this was not enough. They developed the Catskill system, which collects water from both the Hudson watershed and the Delaware watershed, sending it in aqueducts all the way down through to the Croton watershed and down to the city. A phenomenally impressive feat of engineering. So this is the Ashokan Reservoir in the Catskills, and that's a relatively recent photograph, which is why it's looking very nice and full, because there's an abundant amount of water in that right now. And this is just here. This is actually the New Croton Dam at the bottom of the New Croton Reservoir here, which is one of almost the most southerly reservoir. There's the old Croton Aqueduct and now the New Croton Aqueduct, which comes down from that. I took that photograph myself. It's just an amazingly beautiful piece of engineering, this thing here. It's like, that was built around about 1920s. So this is that, remember what David Ryan told me when I was a graduate student about that jump in precipitation that occurred in New York City in the early 1970s? Well, it turns out it wasn't just New York City. It was the whole, it was also occurred over the Catskill Mountains and much of the eastern part of the United States as well. So this is rain gauge data going back to 1900. The drought that exercises the attentions of the water engineers in New York City is one that occurred from about 1962 to 1966. It was pretty much a year-round drought, and there's no seasonal cycle of rainfall around here. Every season pretty much gets the same. And that drought occurred in pretty much every season in the 1960s. And And then immediately, not quite immediately after that, but around about the early 1970s, you had this enormous jump in rain and snow, and we've been living in that high precipitation part ever since. It hasn't ever gone back to what it was before then. So they, nonetheless, we had, after we published this paper last year, and there was a companion paper where we looked at a 500-year tree ring record for the Hudson Valley and the Catskills, which some of my colleagues at the tree ring lab at Lamont did, and that shows that actually this is part of a 500-year-long wetting trend. And the head of the New York City water supply somehow found out about these papers and invited me and Neil Pedersen, the tree ring guy, to the water headquarters at the Kensico Dam to talk to the engineers and the people in charge of interbasin water transfers with the Delaware River and so on. Because they're under a tremendous amount of pressure, given this wet, to run the reservoirs more empty. The rafting industry wants more water in the rivers in the Catskills. The sports fishing industry wants more water in the rivers. The communities want the dams less, the reservoirs less full for flood control, especially after Hurricane Irene. So the city is under tremendous pressure to release more water. And so we talked about this, and we talked about the 60s drought and how we can't say why that happened at all. And that this is like a part of a long-term wetting trend that we also can't really explain. It doesn't fit into ocean forcing or anything like that. And the head of the water supply was absolutely delighted with this, because this was like all he needed to know in order to continue planning for drought. Because the city lives in fear that something like this is going to come back. It's much warmer now than it was then. Water demand has gone up a lot than that. All they needed to know was this was an entirely unpredictable event, that it could begin tomorrow and you would never have no advance warning, and that was enough that they would not make any decision to run the reservoirs more empty than they currently are. So that turned out to be rather actionable.
Question?
Yeah.
Has this excess of rain over the last 30 years, does it raise the level of the rivers in New York, the Hudson and the East River?
Well, it wouldn't. Well, I mean, it wouldn't around the city because that's all very tidally controlled, right?
I see.
But further up beyond it definitely has. I mean, because we did, as part of the work there, we did a flow reconstruction of the Hudson River Valley the Hudson River north of Albany, and you can definitely see in that the flow did go up. Yeah. And the flow has apparently been increasing for 500 years. So this wetting that occurred in the early 1970s, we did the same thing. We looked to see whether the climate model forced by observed SSTs could reproduce the 60s drought and the shift to wetter. It can't. We looked to see whether the CMIP3 models, when you put in changes in radiative forcing and increasing CO2, do they make it wetter? No, they don't. They make it only very, very, very slightly wetter around here. So there was no evidence that this was in any way ocean-forced or radiatively forced. But there was like this intriguing piece of evidence that I came across almost by chance, that at that time in the early 1970s, there was a strengthening of the storm track across pretty much the whole North Pacific, North America, and North Atlantic. So Edmund Chang wrote a paper about this in 2002, where he showed this in NCEP reanalysis data. If you just do the first EOF of eddy meridional velocity variance, high-pass filtered, you find that there's a strengthening of the whole Pacific, North America, Atlantic storm track. And he wrote in that paper, that's the Chang and Fu one, that this must be a problem with the reanalysis. So then he teamed up with Neely Harnick, she became a postdoc of mine just after that. And they looked at it again and they thought, well, let's find out what's wrong with the reanalysis. And they went back to the radiosonde data, trying to find out something that caused an artificial strengthening of the storm track in the early 1970s. And they found that it's just in the radiosonde data. There didn't seem to be anything wrong with the radiosonde data. It wasn't a reanalysis product. You could just look at it in the raw radiosonde data. So they said it must be something that is actually real. So, and then I found that if you actually just compute a measure of the reanalysis upper tropospheric meridional velocity variance right over the Catskill Mountains and compare it with precipitation over the Catskill Mountains, they match each other quite well. And you can see an earlier period, the 60s drought is in here, and then in the early 1970s, it's mostly positive since then. That's actually right over the Catskill Mountains. And then the maps, if you just take the later period minus the earlier period, and this is upper tropospheric meridional velocity variance, you see a positive over here, over the Pacific, over North America, over the Atlantic, spring, fall. And then what these pictures are the same thing, but now they're taken from the 20th century reanalysis. Now that's important because the 20th century reanalysis from Gil Compo, the University of Colorado, it's a NOAA product, only uses surface pressure data. It does not use radiosonde data or anything else like that. It only uses surface pressure. And you find this strengthening in the surface pressure data too. It's a muted version of what you find in the full reanalysis, but it's there. So it appears in the reanalysis, it appears in the radiosonde data, and it appears in surface pressure data. And it looks like the same pattern. It's the Pacific, the Atlantic, and the storm track over North America, the whole hemispheric storm track strengthening in the early 1970s, and then staying that strong up to now. And that seems to have had a precipitation impact in the northeastern United States. Now, that doesn't line up with any of the other regime shifts we know of. It's before the 1976 Pacific shift. It does correlate with the beginning of the upward trend in the North Atlantic Oscillation, but as the NAO then started trending in the opposite direction in the late 1990s, whereas this storm track strengthening just continued. However, and it's also not the NAO because the NAO induces no storm track variability over the northeastern US. Its storm track variability is over the eastern part of the Atlantic and Europe. So it's not directly related to the NAO. It's some other type of phenomenon that seems to be no one pays any attention to it. It seems to be sort of the eccentric uncle of the climate family. But I would be very curious if anyone can explain what this kind of thing is. My hunch is that this is just internal decadal variability of the atmosphere working entirely on its own. And, but I certainly can't prove that. But we're trying to look now by running just an atmosphere model entirely on its own for 10,000 years and see whether we can get multi-decadal variability of an atmospheric storm track that doesn't involve the ocean or anything else, and we'll see. Okay, so next, Northeast Brazil, the Sertão. Northeast Brazil is a climate oddity because it's about one of the few areas in the world where you have a semi-arid area to the west of a warm tropical ocean. And it's a tiny little corner right at the edge of northeast Brazil, and it's got right along the coast there's some nice wet areas, but if you go inland it's like a real desert. If you've ever been there, I was able to go there several years ago, and it really is quite a remarkable area, and it is about the poorest area of Brazil and has been endlessly producing and still does rural migrants to the cities of northeast Brazil and to southeastern and to the southern industrial parts of Brazil as well. So when you look at precipitation in this area, 1900 on, again it's GPCC, and put that together with what the model produces with global sea surface temperature forcing, we do really rather well here. And you can see that there was a drought here, say, for example, in the late 70s, early 80s, a very wet period in the 1920s, and a lot else going on as well. But if you take the tropical Pacific sea surface temperature forcing only one, then there's no matchup between the model and the the observations. In this case, I plotted the individual ensemble members as these little thin lines. I didn't plot the spread as shading, and the reason I did that is because they, with global sea surface temperature forcing, they move so closely together. Each ensemble member in the early 1980s produces this really severe drought. So they're so tight that you can actually plot them, and it doesn't look like a big bunch of spaghetti. The ocean control is so strong in this tropical region, but apparently it's not coming from the tropical Pacific, because the tropical Pacific on its own doesn't do very well. This has been noticed before by many people. Alessandro Giannini at the IRI did this had a picture like this from 1950 to 2000. So because we have these much longer atmosphere model runs, we were able to extend this back to 1900. Actually, we can extend it back even further to the 1850s, because Fortaleza, the big city in northeast Brazil, has a rain gauge that looks reliable that goes back at least to the 1860s, but there's just like the one there. This is a collection of rain gauges from 1900 now. And of course, this actually was one of the first things that people noticed in seasonal intraannual prediction. There were a load of papers by Stefan Hastenrath and Mora and Shukla in the 1980s that showed this link between northeast Brazil and the tropical Atlantic. And when you take the observed precipitation in this region, and this is a regression, these are not correlation coefficients, so this is actually in units of Kelvin or something like that, or maybe it's standardized or whatever. But when it's wet in northeast Brazil, which is this region here, you have this dipole of sea surface temperatures across the tropical Atlantic. So when it's wet, it's warm in the south, and cold in the north. So this is shifting the ITCZ down toward, which normally is sitting north of northeast Brazil. When it's warm in the South Atlantic, the ITCZ is located further to the south, and that's what brings heavy rains to northeastern Brazil. And in the model, you get that as well, and you can see that there is some connection to the tropical Pacific Ocean, but apparently from what we see, that we can't simulate this well unless we have with only the Pacific. It's this Atlantic influence that is strong, the strong one there. So the maps for this case. So the 1920s, very wet time. This is the sea surface temperature, just averaged out during the pluvial of the early mid-1920s, and you can see the dipole in the tropical Atlantic there. And then about the most severe drought of the 20th century was in the late 70s to early 80s. There it is. And you can see the opposite sign sea surface temperature anomaly in the Atlantic Ocean. The Pacific is kind of doing the same thing in both of those cases. So the fact that the precipitation is quite different, this is the model renditions of the same thing, observations and model. The fact that they're doing different things in northeast Brazil, despite both being warm in the tropical Pacific, is because this Atlantic dipole is the dominant influence there. So the previous work on this on northeast Brazil has really been looking at seasonal interannual prediction, but when we look at the decadal variations, which are really quite strong in that region, we're seeing the same thing again. It's the decadal variability of the tropical Atlantic sea surface temperatures that are controlling that. Okay, so 1, 2, 3, 4, fourth area. Southeast, this is the last one of the Americas. So Southeast South America. These are pictures of the other Dust Bowl, the lesser known Dust Bowl, the Pampas 1930s Dust Bowl. And there was a period of severe wind erosion that occurred in Argentina, in southern Brazil, Argentina, Uruguay in the 1930s at exactly the same time as that was occurring in North America. This was not at that time an agriculturally intensive area, but it was ranched. There was a little bit of agriculture. There hasn't been a lot written about this, but it does appear you can see this event in the Antarctic ice core, because there's a big slug of dust deposition that I believe has been traced to the pampas that occurs around about the 1930s. But there's quite a bit more work being done, and these are pictures taken from a paper by Tripaldi, who's a geomorphologist who has been dating these what are now fossilized dunes down there. These people seem quite happy about the situation. So this is the precipitation history that you get from Southeast South America. The observed one is black, and you see that this actually doesn't look totally different to the Catskill Mountains. It went through a wetting in the early mid-1970s, and it's stayed wet ever since. This is the drought that occurred in the 1930s. This is when the Pampas Dust Bowl occurred. This wet trend that has occurred is important in your daily life, because, as in your daily life, because this has allowed a phenomenal expansion of agriculture in Argentina, Brazil, and Uruguay into what were formerly semi-arid areas that have now, because of this wet trend, essentially become subhumid. And this has become one of the main producers of soybeans for the world. Most of these soybeans are actually being exported to Asia now, but it's a key part of the global agricultural food supply that we did not have before the 1970s. This is all rain-fed agriculture. They are not irrigating there, and they would not have been able to do this before the 1970s, but now they are. And the question that comes up down there is this wet trend going to continue? Obviously, the farmers want this wet trend to continue. Argentina and Uruguay and Brazil want this wet trend to continue because this has been great for their economy. But in order to work that out, you've got to come up with some explanation for why it's happening. And it does remain a bit of a mystery. As you can see, our model, the blue one, does get a wet period out here in the 70s and 80s. But our model, and other models too, then it starts going dry after 1998. And the reason for that is, as I'll show you in a bit, is that the shift between this drier period in the middle of the century and this wet period over here was again related to sea surface temperatures. Partly that's the warm El Nino-like conditions in the late 70s, 80s, and 90s, and partly it's the Atlantic multi-decadal oscillation that expresses an influence down here. But ENSO and the AMO started shifting in the late
Well, that helps, but, so what's the role of the mountains, though? You expect to have wet on the west coast, dry in the interior when you get far enough south there because of the rain shadow effect.
Yeah.
Is that changed entirely during those wet years?
Well, that effect would be there for the mean precipitation. So it's dry because it's in a rain shadow if you're far enough south down here.
It's diminished in some way.
So, well, these anomalies are a little bit north of that. The main source of moisture for these regions is winds that are coming through the Amazon and heading south, because they can't get moisture from the Pacific because the mountains. So their moisture supply is coming from the Atlantic, and that's what the waves are modulating, that amount of moisture supply from the Atlantic. Okay, but we can't, despite the influence of the Atlantic and the Pacific and the ozone depletion, we still can't explain why it's still staying wet there. So is that another case of just fortunate atmospheric variability continuing it? I don't know. So a little bit about the Pacific Decadal and ENSO. This is a lot of pictures, but it's relatively simple, like all of this. So these are sea surface temperature over the ocean and precipitation anomalies over the land composited for the warm phase of the Pacific Decadal Oscillation, the cold phase, and then these ones are the warm phase of Niño 3-4 and the cold phase of Niño 3-4. So these are really emphasizing interannual variability. These are emphasizing decadal variability, okay? What I want to point out is just how similar these are. So a warm El Nino event has a precipitation pattern over the Americas, wet, dry, very similar to what a warm Pacific Decadal Oscillation does. Warm, dry, wet, dry, wet, dry. And there are many similarities in other parts of the world too, including over Africa. And then over here is the model version of exactly the same. The model was run over exactly the same time period, so we can do the same compositing. And the model can reproduce that kind of thing. So I just don't want to think there's anything different to the Pacific Decadal Oscillation other than ENSO. It's just a low frequency realization of the El Nino Southern Oscillation, and it's a first order, its precipitation anomalies are just the same as what you get out of El Nino and La Nina events. So the physical origin of this decadal variability is really not different, and the physical expression of it is really not different to what the tropical Pacific does to the world on just on a year-to-year, season-to-season, year-to-year basis. So that's simple, and it's a useful simplification, I think. Okay, Eastern Mediterranean. So in this case, this is Syria. Yeah. We're going to get back to that. Syria, the Mediterranean went through a late 20th century drying trend that has ameliorated a little bit, but this is the 3 decades over which it was the worst, from the early 60s, the strongest drying trend from the early 60s to the 1990s, based on UEA precipitation data, and this was very widespread. Spain, North Africa, Italy, the whole northern shore of the Mediterranean, and over there into the Middle East. And the question there is, well, is this also decadal variability, or is there some evidence that this is due to climate change? Because if you remember the first map I showed you, the Mediterranean is one region where the models predict there will be a significant amount of drying due to rising greenhouse gases. Well, if you look at the first pattern of EOF, oh, I'm sorry, it's an EOF, that's complicated analysis, so I'm violating my rule for this talk. But anyway, this is the dominant pattern of precipitation variability in the Mediterranean section. In the Mediterranean sector, and it looks very much like the drying trend that I just showed you. The spatial pattern is extremely similar. There's a difference in Israel, Jordan, parts of Syria, which is wet when the rest is dry, whereas the observed drying trend was dry in this region and over there. And this explains about 25% of the total variance. So what is that pattern? Well, that is the precipitation, a pattern, precipitation associated with the North Atlantic Oscillation. So the North Atlantic Oscillation is the leading mode of atmospheric variability in the North Atlantic sector. And in its positive state, it creates high pressure, this is sea level pressure, over in the Azores region and over the Mediterranean region. And if you look at the time series of the North Atlantic Oscillation, going back to 1900 up to 2000 and something or other, and you compare that with the time series of that first pattern of variability of precipitation over the Mediterranean, they match each other extremely well. So the precipitation has been inverted here. So this was the 60s to 90s trend towards a positive NAO that went along with drying in the Mediterranean, and then some amelioration of that recently. So the precipitation in this region is very, very strongly controlled by this North Atlantic Oscillation, which is a hugely powerful mode of natural variability, internally rooted in atmospheric dynamics. So is all that is going on. So this is a correlation of rain gauge data with the NAO index. So when the NAO is positive, you have reduced precipitation across this whole region, but then increased precipitation in Israel, Jordan, Egypt. Not as much precipitation there at all. I think I've made the point about the NAO control on Mediterranean precipitation. So how would we then try to work out whether that explains everything that has occurred in Mediterranean precipitation over the last several decades? There are a number of ways of doing that. If you're just going to be using data, one thing to do is you can just project it on some index of force change like global mean surface air temperature. There are complicated ways involving signal noise, EOFs. And then another way of doing it is projecting precipitation on time series of greenhouse gas radiative forcing, which is this black line here. So we did all three, and they all come back with essentially the same result, and that is like this. So these go up. These do go up a bit more recently through 2003-04. This is again the total trend over the last 4 decades. This is when you've just regressed on the index of greenhouse gas increases. This is that first EOF I showed you. So this is the NAO pattern of variability. This then is the difference between the total and this. So if you take away from the total the part that correlates with the increase in greenhouse gases, you should end up with a part that looks like natural variability. So that hopefully should look like this. And it does. But what you see here, and what is interesting, is that the part of the total trend over here in the eastern Mediterranean, the drying, cannot be explained in terms of the NAO variability, because the NAO actually, when it goes positive, the NAO makes that part of the eastern Mediterranean wet, and that part of the eastern Mediterranean has been drying. So what this analysis does, and it does the same if you do the signal noise EOF, and however you do it, it all comes back the same way, that the drying that has occurred in the eastern part of the Mediterranean is a response to rising greenhouse gases. The drying that occurred in Spain, Italy, and and other parts of the regions is more evenly split between natural variability and greenhouse gas increase. But in the Mediterranean, it's dominated by the rising greenhouse gases. So now we've got to one example, we're on example number 5 or something, where it does seem that climate change is appearing, and what we're seeing is not just decadal variability. To just replot that in terms of percent, this over here in the eastern Mediterranean is about a 15% reduction in precipitation, which is quite significant. So Syria is, of course, of tremendous concern right now. If you look at all Syria precipitation, there is a steady decline. It's not that impressive, but they had a very severe drought in 2006, 7, 8, around about that period. And this shows up in, there aren't many rain gauge data available in Syria, but here are two of them where it shows up. This seems to be a funny data point, but here are two of them where it seems to show up down here. So this was kind of as severe as any that had occurred before, especially in terms of 3 years running. There was something like that happened in the late 1950s, but since then Syria has a much larger population, and also in the intervening decades there was a decision by the Assad regime to make Syria a food-independent country, and it expanded its agricultural sector to trying to grow all of its own food. It became more dependent on its agricultural economy in this intervening years at the same time as its population grew, etc., etc. And Tom Friedman in the New York Times wrote an article last year, it was 2012, where he pointed out the possible role of climate change in igniting some of the Arab revolts that occurred. And he has a film that's going to be coming out about this soon, or a TV show that's going to be coming out about this soon. There seems to be no doubt about this, because at the time the newspapers were absolutely full of stories of farmers and their families in the northern part of Syria leaving their homes, and as the stories went, we can survive 1 year of drought, we can survive maybe 2, but if it gets to 3, there's nothing, that we have no reserves left, we have to leave. And they did, and working with an undergraduate at Columbia who had actually traveled in the region the year before last, and she put together this plot from data that's readily available data about migration so this is a timeline of events. So the first thing that happened in Syria was the Iraq War, and then Syria became swamped with refugees from Iraq. They reached about 1.5 million by the time you got to 2010, and they have not returned. I suppose they have been returning recently, but by the time the war began in Syria, they had not. And then the number of refugees from the northern part of Syria, so internal Syrian refugees, to the cities of Syria equaled that by the time you got through to 2010. So it was over 1 million. And those numbers come from the United Nations and various other relief organizations that were working those numbers up. The drought was in this period here, and this part effectively doubled the drought effectively doubled the refugee population in the cities of Syria. So the total urban population in Syria began at about 13.8 million in 2003, 8.9 million in 2002, and climbed to 13.8 million by the time the war began. Of those, the population increase would have been about 1.5 million at the 2.5% birth rate, and that was equaled by Iraqi refugees and Syrian refugees. So it is really hard to prove that the cities where these migrants went to was where the uprising began, but colloquially that does stand up in the where we know the cities where the migrants ended up were the cities where the uprising began. A lot of the urban population, the core urban middle-class population in Syria was complaining about rural refugees in Syria inciting this revolt. So it probably played a role. The war in Iraq probably played an equally large role as well, and then the ongoing dynamic of events related to Syria and the wider region. But the evidence is there that this drought, which we have shown became more likely because of climate change, was one of the factors that played a role. So finally, in East Africa is one place in the world where for a decade or more now, famine and mass starvation and death is occurring. That's not that common in the world anymore, but East Africa, Somalia, Southern Sudan and so on is one place. So the observed precipitation history, we have about 100 years of rain gauge data in East Africa. That's the bars here. This is the recent drought. So since about the end of the 1990s, there's been a precipitous decline in precipitation in East Africa that is unprecedented, although there have been some extended droughts in East Africa before. And then that's from the rain gauge data. These are various satellite products that begin in the 70s, early 80s. There's been some low-pass filtering applied, so that's why they begin in the early 80s. And the satellites actually make this decline in precipitation much more extreme than the rain gauge data does. But all the data indicates that this drought has been ongoing. And, you know, one of the reviewers of this paper said, can you prove that there really was a drought? It's like, duh, you know, I mean, it's, you know, anyone the IRI has lots of people who work in this region. I mean, there's tons of this is observed. You don't need to know, you know, you don't need a weatherman to know which way the wind blows. You don't need a weatherman to know that this drought has been going on in East Africa for a long period of time. But anyway, there you are. And if you take precipitation within this region and regress it sea surface temperature, you find, again, our familiar Pacific pattern. When it's wet in this region, you tend to have this cool phase of the Pacific decadal variability. If you do that instead of regression, you do that on SST composites, so you composite all the wet years and composite all the dry years and do a difference, dry minus wet. Again, you find this Pacific decadal pattern. Interestingly, not so much in the Indian Ocean. It seems like the Pacific is the dominant one here. And Brad Lyon and Dave DeWitt at the IRI recently published two very nice papers that show this. So it seems the general rule is, and the latter part of the is no exception, the general rule is that drought in East Africa is tropically Pacific driven. On the other hand, nonetheless, the East African drought is one which is commonly attributed to climate change, including by my boss, Jeff Sachs, the head of the Earth Institute, and various other people. It's always being invoked as climate change is the cause of it. But actually, it turns out that climate models predict that East Africa will get wetter. So this is the trend over the historical period, this black line for the CMIP5 models, and they show it just getting very, very little wetter. Whereas this, again, the bars here are what actually happened. So, and then this is the precipitation trend that has actually happened from 79 to 2008 from satellite data. There's the East African drought, and this is the signal of the Pacific decadal variability with cold temperatures here. Going forward from this period out to the future, this is what the CMIP5 models project will happen. So they project that this region, you can't really see it there, but they do project that it's going to get wetter there as part of an increased precipitation in the tropical Pacific ITCZ here. So what has happened over the last 3 decades is completely opposite to what the CMIP5 models project should be happening as a consequence of climate change. So what do you believe in that case? Well, primarily that difference is because what's been going on in East Africa for the last few decades is natural variability. But these coupled models, first of all, the SST force models, so if you just take the atmosphere models and put the sea surface temperature underneath them, they do, this is from the models from the CMIP5 archive, they do produce a drying here. So the CMIP5 ensemble mean is the black line here. So when you tell them what the sea surface temperature is, they knew that after the 97, 98, it should get drier there. So the atmosphere models are doing all right in this region. And they're saying it gets drier there because the tropical Pacific gets cold. So again, that's the end of the 97, 98 El Nino, the shift to the colder state of the tropical Pacific. As part of the global precipitation response to that, you have the drying of Western North America is one, but drying of Eastern Africa is another. But when you look at these coupled models, they do a terrible job. None of them reproduce, not one of the CMIP-5 models reproduces that connection between Pacific decadal variability and dry in East Africa. They just really sort of don't have Pacific decadal variability very realistically. To the extent they have any Pacific decadal variability, they do not connect it to East Africa correctly. So the models just do not, the coupled GCMs do not represent this type of behavior. And
how do you couple something by specifying a CCSST?
no, the coupled models don't. The coupled models don't have this connection between East Africa and the Pacific Ocean. The atmosphere models, just the atmosphere models, if you give them the sea surface temperature history, they correctly can connect the tropical Pacific to East Africa when you impose the SST under the atmosphere. When you take that atmosphere model, couple an ocean model with it, it's wrong.
But you're not specifying SST
No,
in the couple case.
it's computing its own.
Yeah.
So you're just looking to see whether they get that type of behavior,
But
and they don't.
just because they can't make the PDO.
It's partly because they can't make the PDO, but it's also partly this. So in East Africa, there are two precipitation maximums. There's a big peak in the early part of the year and a secondary peak in the fall. So that's the bars are the actual data from rain gauges. This is what the models do when the SST is imposed. They get that kind of right. Now, if you take the coupled GCMs where they're computing their own SSTs and so on, they do this. So they actually get a peak here, which is weaker than a second peak, which is way in the end of the year. So the coupled GCMs are incorrectly modeling the seasonal cycle over East Africa. And I would imagine that is one reason. The fact that they cannot get the mean climate right in this region is one reason why they don't get the variability right. The other reason would be they're not getting that Pacific decadal variability right. But the fact that they can't get the mean climate right in this region makes you really wonder whether their prediction that it's going to get wetter in this region is correct. Because they're just not living in the right climate world. This is not the case if you're thinking about Western North America or Northeast Brazil or something like that. There the models can get the seasonal cycles right, and you'd probably have some confidence in their projections of the future. But in this very, very key region, because it's the one region in the world where hundreds of thousands of people are dying because of drought and starvation, it's a politically vulnerable region. It's one where US security forces are continually paying attention to because of the relation to international security. This is one place where these CMIP-5 models seem to do an incredibly bad job. And they're making a prediction of the future that it's going to get wetter when the 20th century has just got drier. Up to now has just got drier. So I think probably all bets are off within that region, but you would not want any of the aid agencies basing their decisions on the current state of the CMIP-5 models in that region, but apparently they are. Okay, I should stop. I think this is the last slide, but I just wanted to point out, if you haven't got the point by now, that there are these global hydroclimate regimes that, when you're looking at East Africa and South America, Northeast Brazil, they tend to go together or out of phase because much of this is being orchestrated by the Pacific and Atlantic Oceans, and it's creating connections between hemispheres, around the hemispheres, into what you could call, regimes of hydroclimate. Again, Brad Line and Dave DeWitt have a really nice paper out in 2013, just published, that is about that. I think I'll miss that because I must be over time, right? Yep. A little. Okay. The point of the previous slide, which I won't show you because it takes a long time to explain, is that this decadal variability is really important, and it's going to carry on into the future. And much of what we will experience in the future is going to be, or all of what we experience is going to be some mix of radiatively forced change and the continually evolving decadal variability. Now, a lot of people like to say, well, the radiative force trend, how, you know, is it significant? And there was a couple of papers by Clara Dessa recently focused on North America where she claims that, you know, there's no statistically significant precipitation trends that appear anywhere over North America over the 21st century. I'm probably misphrasing that, but that's kind of the implication. And they're looking for like 95%, you know, level significance. You know, for those of us who actually come out of a seasonal interannual prediction environment, when we do seasonal predictions, we don't look for statistical significance. When we issue forecasts for what precipitation is going to be for the next season, it's presented in terms of probabilities of terciles. You say there's a 60% chance that precipitation in the southwest US this coming winter will be in the lower tercile, or a 30% chance it will be in the middle tercile. You know, that's the way that seasonal predictions are done. That may not be statistically significant, but it's considered a useful forecast. And what I did there was like looking at, well, we have this past decadal variability. We know this really matters. We can have history that shows that those decadal variations matter. They might fall below statistical significance, but they matter. So why don't we look at climate change and try to relate it to terciles of the decadal precipitation? When does the radiatively forced change start shifting the probability of terciles, of falling into terciles? And the basic conclusion is that, like, if you are in Arizona, New Mexico, by the next decade or two, the probability of being in the drier tercile goes from being a third, which is what you'd expect if it was just continuing natural variability, to like 50–60%. So, you know, there might not be statistical significance by Clara Dessa's standards, but by the standards of having to adapt to decadal variability, that is significant. If you can expect that 6 of your next winters are going to be in the lower third of the 20th historical distribution of the 20th century, that's kind of a worrying forecast, but that's what it does say. By about 2030, 2040, you're sort of getting to that. The only other point, so, you know, much of what his global decadal variability, the one areas I looked at, is related to the Pacific and Atlantic, and we can explain much of that, but what really I find a mystery is some of these ones like long wetting trends here, Northeast North America or Southeast South America, where we've got these unexplained, very long trends. They're at the very, very limit of what atmosphere models can do. And are they just, you know, unusual atmospheric variability doing this and it's just unusual, or is there really something else going on there that those trends are saying us that our models do not have sufficient decade to centennial variability? There should be more. Is there some other kind of mode of forcing that we're missing? Is some of these century-long trends related to sort of coming out of the Little Ice Age? Could they even be orbitally forced? I mean, it's possible. So I think that's a sort of an ongoing mystery that's really worth looking at. So I'll stop there. Thank you.